So hey, this is Luca from Yelp, and I know it's late in the afternoon. I will try to be not too boring. And so I work in a team that is called Core Machine Learning. Previously, I was in user location intelligence, and this project is related to the work I did there. I will speak today about real-time store visit predictions at scale. It's a Flink use case. And I'd like to focus on actually how great Flink was to enable a data team like ours to do stream processing. So what can you expect from this? First of all, I think it's interesting to outline the product that we built. So I will speak about the algorithm that we used, the problems we solved, and then how we solved them using Flink API and Flink constructs. And finally, I'd like to say a few words about the impact that Flink had on our team. So as I said before, I work for Yelp. Yelp mission is to connect people with great local businesses. And in this context, we built a new type of push notifications. So the one you see in this picture is a notification whose objective is to suggest the best nearby businesses to Yelp users. In this example, it's asking to me, to myself, Luca, are you near Creator? Creator is a burger place close to Yelp, actually. And as a matter of fact, I was there. So this notification, seemingly so simple, requires quite a bit of work in the background, actually. If you think about it, it needs to be first timely and relevant. It needs to be timely because if we notify the user when it's too late, then they might be already far from the business, they might be already home, so we don't want that. So we need to have low latency. We need to use a framework with low latency, and it needs to be relevant because we want to provide a very good suggestion. And that means that we had to build a machine learning model for this. A quick note, many users, Yelp users opt to share their location information with us to benefit of this personalized recommendations, but whoever wants to keep a low profile can just very easily go in the app and deactivate the setting. So in order to understand the problem, let's start from to have a look at the input data. The one you see here is what we call raw pings, raw locations. We sample this location data from Yelp mobile devices. This is instantaneous location, so it's not. It's very hard to do something with this if we don't perform first we need to understand if someone is stopped somewhere for a certain amount of time. So we want to know if someone has a stopover or what we call a visit. And a visit would be, it's safe to assume in this picture that a visit would be where most pings are grouped because someone might have been there for a while, and so we got multiple samples from there, so we call this a visit. The next step, we need to retrieve a list of candidate businesses that the user might be interested in visiting or might actually be visiting. And we need to rank them and get the best one for that specific user at that specific location. So to answer this question, we built a machine learning model. For who's curious, it's an XGBoost model. And we're trying to answer the question, given this input location and this user, so for example, Luca at California Night Street, what's the best business that Luca might be visiting among the list of these candidate businesses? So to build this, let's have a look at the final system overview, and then we'll dive into details. To your left, you can see the input data. That's thousands of pings per second coming through Yelp data pipeline. You might have heard of the data pipeline in some other talks. We get all this data input into our Flink job, where real-time clustering happens. And Flink will delegate the machine learning inference to an external service, Python service. There's a reason for this. We had it already built there, so that's why we didn't bring it in. But we use a killer feature at this point that it was actually preventing us to scale before. We use Flink Async I to scale our requests in concomitance with Scala dispatch. When we get the data back, we put the predictions, we link them to the original visits, and we create an object that is called store visit. We put it back into the Yelp data pipeline so that other teams can use the data, for example, for sending notifications. And right, so how did we solve how did we cluster things, group pings together in Flink? It was soon evident to us that we couldn't wait for too many pings before deciding if we have a stopover, because we want to have low latency. So we ran some data analysis, and we came up, so we couldn't run any complex clustering. We found out that very often a couple of pings is enough. So we started looking at pairs of consecutive pings at a time, and we noticed that we ran some analysis. We came up with some values. So if 2 pings are closer than d meters and they're further away in time than t minutes, then there's a very good chance that's an actual visit. And we try to lower false positives by increasing the time so that we don't detect a visit if someone is just waiting at a bus stop. And in this example, Flink is already emitting an arrival visit as soon as the second ping is received. So the first one at 3:21, 3:27, we emit an arrival visit in the stream so that notifications team can already do something with it. If you notice, there's the starting time, but the parting time is unknown, so it's plus infinity. The third ping will be put in the same visit, but we don't know when the user will leave. But as soon as we get a ping that is further than d meters plus epsilon from the visit, then at this point we know that we can close the previous visit. So we emit a departure visit from 3:21 to 3:30. We know when the departure happened, and we can tag this ping as a transit ping. All this happens in a Flink process window function, so it's a custom process window function. And before detailing a few other constructs, let's go through an example just to solidify the concept. So as you can see, this is the 2 pings you saw before. We use a global window for each user. So if you think about it, our windows are not time-based. There's not sliding based on time, but they want to always analyze pairs of consecutive pings. So we decided to go with a global window. We assign the pings to this global window, and whenever we get a new ping, we will evict the old one, and we put the new one in. We run the clustering. We can detect, is it an arrival, is it a visit, departure visit? We need state for doing this, of course. We need to remember if a user was already somewhere, if it's transiting or arrived somewhere else. And so we go on like this, always looking at pairs of pings. And here you can see we detect another visit because these two are very close, closer than d meters away. So we built a custom trigger to do this, and it's called onAnyPing trigger. It just fires processing every time we receive a ping, because we always make sure to leave at least a ping in the global window, so whenever we receive a second one, we cluster, or we group. And we have to always leave a ping in the global window because of some Flink internals. If we don't leave any data in it and it's empty, then we're unable to purge the window based on timeouts. And we really want the window to be purged, the data to be purged in various cases. So if the user has deactivated the feature, they uninstall the Yelp app, so we have a timeout. If we see no data for a while, we purge everything, and we avoid going out of memory. Evictor, we just use the default evictor, so with a count of 1, so that we always leave at least a ping in the global window, as I said before, and the outcome would be the one that you see in the picture to your right. Now, the biggest challenge, especially for a team like ours that we weren't versed in stream processing, was time, handling time. You all know about the skew between event time and processing time, but our messages were created on mobile, and mobiles are very, very far from backend. So mobiles have also some weird behaviors, like mobiles can go offline, completely offline. The data is being collected before maybe, they go offline for days. So you would get data that is hours, days, or even, I don't know, weeks old. And user tweak clocks, or mobiles have wrong clocks, so we can even get data that is 45 years old because the clock is completely off. At this point, you understand we had a lot of data that was really unusable because you don't want to notify for a visit that happened last week. So what we did was we kind of implemented our own custom event time processing with no allowed lateness, so we decided we drop everything that is too late. And to do that, we built, it was very, very easy with Flink. We just built a late ping evictor, and anytime we see a ping that is too late, so in this example, you can see the event time is before the one of the previous ping. And this one is too late, so it gets evicted. It never sees the window. It actually got to the backend at 3:24, which is after the green one. But it was created on mobiles before. And so the outcome would be our window, we only see the green pings. I will perform clustering on these. Of course, there's a drop in recall because we have sometimes, we're dropping good data sometimes. That is just having a little bit of skew, not days, not hours, but maybe sub-second out of orderness. But we ran analysis again, and it was, we could accept that for simplicity. Now, a few words about the model that we use. So as you remember, Flink is outsourcing the model to our Python service. The Python service is, the first step was to get all the candidate businesses. It's relying on our search infrastructure that runs on Elasticsearch. And we're also using feature rows that are stored in Elasticsearch as well. And they end up there. It's an online feature store. They end up there. We use Flink for that as well, just different jobs. And our model will run through all this data. We will get a confidence score in output, and we pick the business with the highest confidence score. In this example, you can see Creator was a business. To have some intuition about the features themselves, just because maybe you might be curious, I put a couple here, like distance is a very good feature to understand if a user is somewhere or is intention to go somewhere, because among a bunch of bars, the closest one is very likely to be the one. Or directions is what we call, it's a feature that we call if someone has asked for directions within the Yelp app, like in the previous hour, in the previous week, in the previous month. Because it means, if I'm asking how to get there, and then I'm close to that neighborhood, then it's very likely I might be there. So that's a very good signal for us. And yeah, all this data gets back to Flink. We put the confidence score in, we create store visits, and we put them back into the, our output stream. So to understand a little bit why Flink was such a breakthrough for my team, we need to understand where we're coming from. So before using Flink, we were heavily relying on Amazon SQS, which is a queue processing mechanism. It implements the producer-consumer paradigm, and basically you can produce a message, consume a message, does not state. So we had to implement our own state that wasn't really working very well, and this clustering algorithm that is even so basic, it wasn't possible before without state. So the first thing is we couldn't do what we're doing now. The second thing, we have an abstraction layer on top of SQS, which is done in Python. Python, due to the global interpreter lock, it can be concurrent, and it's very hard to be parallel. We had some incompatibilities with our stack and some asynchronous libraries. It ended up being a couple of postmortems, so we couldn't really be parallel. We decided to increment the number of processes. We got to a number so high that deployments were taking hours. And finally, SQS, as someone else said in a talk today, leads to duplicate data. And duplicate data in our case means duplicate pushes. So you basically get the same exact push twice in your app, and that's very bad user experience. So we were also intentioned to solve these problems. So how did Flink impact all this? So first of all, we could implement a better clustering. So we had a higher visits recall. a 10x visit recall increase. Huge gain, huge win, and Flink was justified. So yeah, let's do it. We managed to scale up to thousands of machine learning predictions per second at Yelp. And as I said before, we managed to solve our scaling problem. So we went down from hundreds of Python processes to only running 14 Flink instances. Yeah. And finally, all this was cheaper. So there wasn't really a trade-off like this is better, but it costs more. It was like it's cheaper, it's better, it's technically it's great. So our experience was extremely positive, and yeah, the community and mailing lists were incredibly helpful, very welcoming. So I would like to give them a shout out. And yeah, maybe the only trade-off in all this was that developers had to move to Scala. So I think we've seen some talks today about this moving to Python thing, but we had to learn Scala. So that concludes it. We're hiring, so you can come talk to us. There's some links here, and we have about 3 minutes for questions. I think 2 or 3 questions, maybe. Yes?
Let's thank him for the talk. Thank you.
Hi, yes. So you talked about moving from a Python-based pipeline to Flink, which is a Java-based pipeline. Were there any kind of cultural shifts that had to happen? Was there any resistance to switching stacks? Because it's a pretty major stack shift.
Yes, cultural? Like, what do you mean?
So when people are used to coding in Python, and you have to transition them to coding in Java, I'm not sure if you had developers who knew both Python and Java, or you had to train people up to code in Java, or you hired people who knew Java, like how?
Yeah, a very good question. So actually, in our team, since we had it was a data team. We had some data scientists that came from Java, actually. So we had some meetings in which we analyzed the two, and we all had previous Java experience. We thought, well, worst case, we're gonna write very basic. Like we started writing very basic Java, and it was fine. But of course, there was a ramp-up period. But I feel like I've seen many people, and I even mentored, to ramp up and moving from Python to Java with a little bit of background. It generally took 4 to 6 weeks, and it was really fine.
Okay.
So very low cost, I think, to ramp people up. Yeah.
Thank you.
Yeah.
So in the middle of the whole pipeline, you were doing async I/O calls out to Python processes, right? That were doing the feature waiting?
Yes.
So didn't that create the bottleneck where you needed to have a whole bunch of Python processes running to handle the load of the pipeline?
No, actually, maybe I didn't explain it properly, but the bottleneck originally was in place of Flink, the Flink box, we had Python clients. And that, yeah.
But still, wouldn't that be a bottleneck where you'd have to run a lot of Python processes to keep up with the Flink workflow, trying to make all these async I/O calls to them?
Yes, very good observation. So the thing is, it's 2 different stacks, and the client stack, we call it workers, was incompatible with the asynchronous library that we tried. While on the other side, we have services. And at Yelp, we run a lot of services in Python, and we managed to have them. We have multiple processes and multiple workers on that side. So it was a problem on the client side. So actually, that Python service scales up much more than what we see now. It's just we don't have enough data to bring it up even more. But we tried it. We have peaks that are much higher. So we're not scared about it. Yeah.
So this particular Flink job is very highly available, because if you lose for a certain time window, then you cannot reprocess those older events because of this. Those are late events, right? So especially because you have the state and it needs to be checkpointed, and as well, if let's say one of the tasks dies and node dies and all, right? In that case, the checkpoint doesn't move forward. So these are because the Flink is more towards strongly consistent. So did you face the problem of availability of your Flink job,
So this is actually thanks for the question. Very good question. We faced it more before, so that was an improvement. But yes, we faced it. The thing is, if you think about it, if it goes down, we're failing to send push notifications. And there's some mechanism on that side that if you don't, we don't want to harass people with too many, so it's very rare. So if we don't send this type, we have so many other types that might be, so there's never a loss there. On Flink's side, something that amazed that was how available it was. It was really, it's almost always up, and whenever we have issues, as you said, since we need low latency, we generally discard like 20, 30 minutes, whatever the downtime is. We start it again as soon as possible, and it's always worked fine.
Thank you.
Cool, thank you. I'm afraid we're running out of time, but I'm sure you can answer more questions outside if anyone is interested.
You can hit me up later.
Cool. Thank you
Thanks.
again.